So again, this is day 3 of our annual Textile Design Spring Speaker Series. We are the Textile Design programs at Thomas Jefferson University. And we've had a great week. We're thrilled to welcome Dr. Topher Anderson today as our esteemed guest for our finale of our speaker series. Topher is a wonderful alum of Philadelphia University / Thomas Jefferson University. And we're very excited to see what he has to share with us today. So with that, Topher, I'm going to turn it over to you.
All right, thank you, Marcia. Hello, everyone. I'm Topher Anderson. I used to go to Philadelphia University / Thomas Jefferson University, so I'm very familiar with the programs out there and what you guys are working on. And I think there's a couple other people from around the world that are joining in from this. So hopefully we can learn some new stuff about what textile engineering looks like in the future and what technical embroidery can provide that future textiles and what we can do with it, quite frankly. So without further ado, my background is in biomedical engineering and textile engineering. So I look at different bioelectrics and then also how do we put different sensors or different types of measurement reading systems into textiles or flexible electronics so that we can start to use those textiles in new and modern ways. A textile in general has different properties that we've already known, such as visual aesthetic, which is an important one, insulative. Sometimes we have other textiles like geotextiles that interact with the ground to help prevent erosion and things like that. So we're going to go and push those technical textiles one level further and say, what can we do to that textile to make it have interaction, to make it be able to give us information about our environment, and also to be able to provide feedback back and forth to the user and to the wearer. So currently this is coming from ZSK. ZSK, I'm going to go over here, and ZSK is a embroidery machine manufacturer in Germany, one of the best embroidery machine manufacturers in the world. And they work on high-end modern equipment that can be used to put down things like wires or put down circuit boards or some of the other things that we're going to talk about in the presentation. But if we look back, ZSK has a long history of different embroidery machines. So if you think, when I say embroidery machine, you can think of these traditional machines on this slide. On the left-hand side, we have a machine that's a punch card driven machine from Zhang's, which is the Z in ZSK. And then on the right-hand side, we have another a more vintage embroidery machine. So when I say embroidery machines, this is it, but it's also not. We have a lot more that we can do with the machines nowadays with modern textile engineering. So when I say what is a modern embroidery machine, we could start to look at the next type. So this is a more modern embroidery machine. This is called a SGVA. I have a similar model here in the lab called a JGVA. It's just a little smaller, but it's the same thing. But this type of embroidery machine lets you do anything any embroidery machine can do in the ZSK fleet. So that allows you to put wires down, some of the other textile processes that we're going to talk about, 3D printer filament. It allows us to cut around the outside with a hot air cutter, put sequins down, put beads down. Everything can be done on this machine. And so that's really why I use this one as kind of the description of what I'm talking about when I talk about an embroidery machine. It's maybe a little bit bigger than we're used to thinking. Maybe it does a little different things. But if we look at it more as additive textile manufacturing, then I think we start to get a better a workflow and thought process of how we can use these equipment and what we can do with them. So here we have a machine with 3 different heads. You'll see there's 1, 2, 3 heads. The first one's called an F head. The middle one's called a K head, and the outer one's called a W head. So we're going to go through what each one of these does, what the opportunities they bring for textile engineers, and this will allow us to do a lot of different technical processes for fabrics. So if I look at F head, which is the first one over here, we can do normal satin stitches and running stitches, the type of thing that you'd find on a baseball cap, or maybe you'd find it on a shirt, some of that embellishment embroidery, curtains, that type of thing. But we also have a very interesting play here for attachments. And you can see there's 2 different attachments on the head. This allows us to put things down like sequins or cords or hot air cutters, laser cutters, other things that could potentially strap onto this machine to augment the function so that it's not just putting thread down. We can start to put mixed materials down. So I think F-head is a very interesting one, especially again in circuit board stitching and a lot of smart textile applications. K-head here in the middle is an interesting one too. This is the chenille embroidery head. And chenille lets us do chenille stitching or moss stitching, which is a very fluffy stitch that has some interesting volume properties. It also lets us put down chain stitch, so chains of stitchings that are one continuous thread that keeps chaining through each other, kind of like crochet actually, only in scale on a larger machine. And so from this one, we have a lot of opportunities here as well because of the structure of one continuous thread that we can keep looping back and forth inside the textile. And then the last one that we have here is WHead embroidery. Now, WHead, I like to think of wire embroidery, but it does way more than that. We can start putting down different types of wires, of course, but also carbon fiber, fiberglass, tubes. I have a project right now with garden tubes and putting hoses into fabrics for gardening. So if you have any interest in that, reach out afterwards. I can give you some more information because that's an ongoing project. But WHead lets us put bigger, non-traditional things down using a zigzag stitch over top of them. So if we look here at chenille embroidery, this is traditional chenille embroidery. It's a bear, it's kind of an embellishment motif. Chenille is typically used for letterman's jackets, for different types of more vintage-esque textiles, a lot of wearable space as well in that space. But if we look at this, you can start to see inside of this textile, we have a height here. We have a different volume of thread. It's very soft and loopy. And so as ZSK, we look at what can we do? If we can have a machine that produces these in scale and beautifully, can we use that for something new? Can we start to take that same structure and really utilize it to make a new technical textile? And so what we started doing is working with different thread companies to try to create these smart textile threads and use these silver threads or these conductive threads. And so in electrical engineering, if you're thinking about it, if I put a parallel resistor next to another resistor or a parallel conductor next to a conductor, I start to build up conductivity, which is good. You get better signal. But now imagine I could do that in 3 dimensions. And that's what this starts to do. And that's how we start to get really great signals out of it. And so if we look at this, now we have a new material with a new process. What can we do with this new material? How can we use this high conductivity? And a colleague of mine over in Germany works on a lot of this, doing these chenille sensors. And so we started to use these sensors to be able to do heart rate monitors in pieces. So you'll see here we have an A electrode and a B electrode, and then a reference or differential op amp. So what it does essentially is we take a reading from all 3 of these, and then we subtract out this reading, because this reading again is maybe your cell phone going off, or maybe it's some other signal in the room that we don't want to measure. That allows us to get a very crisp and precise reading of heart rate. And you could start to really use this for a lot of different topics, like heart rate is one, but we could also do EEG for brainwave reading. We can do TENS device for electrostimulation to start gently warming up muscles or relaxing muscles in that regard, all using different takes of just this one technology. And so after this, we started looking that there's a whole bunch of things we could do in the technical space. We could start to work with different materials. We could put this in fabrics. We could put this in plastics. I've done a lot of different projects with different materials, even like cheese, putting things down into cheese, which is not typical things that you would think of in textile engineering, but it follows that same kind of mindset of, can I use a new material in a new way in a flexible system? So after this, we started looking at some other different technical pieces. And one of the heads that we have is this W head here that I talked about briefly before. And WHead allows us to put down a functional fiber or a wire or a carbon fiber or a 3D printing filament. And it allows us with a needle and normal stitching thread to stitch a zigzag stitch over top of it. And this zigzag stitch lets us hold these strange materials down into another material, a textile or a plastic or something like that. And so you'll see down here, there's a piece of wire being embroidered down, zigzag stitching over top of that. Now, 2 things move in this. The table moves in X and Y, and that's what creates that zigzag, but also the foot here also moves, and that helps us get very tight corners so that we can go around corners in full automation. So we have 3 different techniques in here for WHead. We have wire embroidery. So this goes up from 63 micron stainless steel wire, even smaller. So that's 1/4 the width of a human hair, all the way up to much thicker wires. We go 24 AWG and even thicker than that. Tailored tube placement lets us put tubes of several millimeters down so we can start to put small garden hoses down into a fabric. And then tailored fiber placement we look at to put carbon fiber, fiberglass, 3D printer filament, flax fibers, anything else down in that technique. So if we go in a little bit more, we can see some of the examples. So here you'll see we have a wire being placed down into this is a scrim material. So this is a really big opportunity because there's a very few ways to really put a wire very secured into a fabric and also very reliably. So even 10, 15 years ago, people were putting down wires in the fabric by hand gluing them using pegboards. There's actually companies that I've been into even in the past 2 years that are still doing that. They have a pegboard where they wrap the wires around and then somebody comes in with a hot glue and they glue the wire down, and that's how they put the wire in. That's archaic. We don't do that anymore. What we do is we use the embroidery stitching machine to be able to put all of these wires down fully automated. And so the turning point for this was with the car companies. And there's a lot of car companies that have started to stitch wires into the preforms for the car seats. So anytime you sit on a car seat heater, chances are it was probably embroidered at this point. And that also opens up the first door of smart textiles in scale. So where smart textiles for the past 10 years has been kind of quiet around the sides, we start to see some of these applications which are in the millions of units in automotive and other applications as well. So wire heating has a lot that we can do with that, and putting heating wires into blankets, into textiles, into curtains, into carpets. The next one over is a biomedical application using tailored fiber placement to be able to put down reinforcement for tissue engineering. So with this one, we can create anisotropic scaffolds. So what that means is if I put just a piece of fabric or biodegradable fabric into a person, it has generally isotropic properties. So that means it tears the same in different directions. It has the same mechanical, it doesn't really stretch much. But with embroidery, we can start to lay strength regions, or we can start to lay regions that have more elasticity, or be able to shape that textile so when we embed it into the body, it has exactly the mechanical properties we're looking for, so it behaves like native tissue. And so this is a really exciting one too, and a whole bunch of different bio applications for creating different types of reinforced scaffolds, as well as putting signals into scaffolds as well, so that we can take data out of them, temperature data or other things. And then finally, here on the right-hand side, we have mixed material. So this is a carbon fiber that we can put things like fiber optics into or wires into, so that we know that if that carbon fiber preform is damaged at all, we can say that this preform is damaged, don't put this part in the plane, keep the plane on the ground and fix this part. Or we can start to do things like putting sensors or integrated heating into it as well, which has some really neat applications in aerospace industry. So you can see, even just with this tailored wire placement technique, we have a lot of opportunities, and the sky's the limit for what the geometries and the end use cases are for these. So one of the ones I start to hear about is, how do I start on this? Like, what is a simple process? So here you'll see a very basic insert for a shirt that has a wire, a heating wire that goes through it. And the way I like to look at this heating wire is it allows for something called thermal shaping or thermal density shaping, which means we can put higher levels of heat by areas that are more exposed to the cold, and then reduce the density of heat in areas that are more protected. And that lets you feel more comfortable when you wear it. So an embroidery from this perspective could be as fast as 20 minutes to set up the file and digitize the file for the wires. We could take something from Adobe Illustrator, a line drawing from there, or a DXF. And then we can let the embroidery machine run this, and half an hour later, you have a part that's ready to go coming off the machine. And you can start to test it, use it, change it, tweak the geometries. And that allows us to really use embroidery as almost like almost how 3D printing is being used to prototype things, only the embroidery is even faster in many cases. We don't have to wait 24 hours for a part to come out. And this part is scaled modularly. So if I want to start scaling this, I can send this out and have this exact part start to be scaled at different manufacturers, or I could even scale it in-house if I want more control over it. So here's a project that we worked on with a company called Antelope, who made an Electro stimulation suit. So this suit you put on, and it has those K-head electrodes, those chenille electrodes the whole way throughout it, such that it starts to gently stimulate your muscle before you go running, and that warms your muscle up. It's like stretching your muscle before you even get on the road. And when you start doing that, your chances of injury are much, much less. And so this is a really interesting part, just showing that you can start to integrate these embroidered electrodes, or these TENS device electrodes, throughout an entire garment and start to have usable and meaningful interaction with the user. So this is a really neat project here that I'd recommend reading about as well. Other ones, so here we have some more concepts for those heating jackets that I was showing 2 or 3 slides ago. And again, you could do different heating jackets in a variety of different ways. You can make it into different shapes. You could do inserts. You could put the wires directly in the fabric. The sky's the limit for what the geometry is that you're using and how you want to play that into the cut and sew process. Another thing that we have to switch gears a little bit is the carbon fiber embroidery, which has been really interesting as a technical textile. So carbon fiber is extraordinarily lightweight and strong and stiff. So what that means is we have some material properties of it that are unlike any other materials. That can be, for its weight, stronger than steel, stronger than aluminum. And we can also work with it because it's a textile. We can start to shape it in very bendable ways that might be cost prohibitive to mill out or machine out. And so here you'll see that there is a carbon fiber toe that pulls down throughout the entire piece. And this is getting zigzag stitched down into a preform for a bike seat. And this bike seat lets you have variable stiffness. So we can start to shape areas of the bike seat to be flexible so it bends a little comfortably underneath where you sit. And we can also have longer pieces of the bike seat where there's higher stiffness. So this was done with a company called Shape. And then we have one of my colleagues in Italy actually is working on developing this type of technology for automotive industries. So we're doing a lot of work in that space of trying to create these new ultra lightweight, strong textiles that we can embroider down. And then afterwards, once we have this preform embroidered, we can then either inject resin into it to create a hard, stiff part, or we could start to use hot presses to consolidate and melt plastic fibers into that such that we can make a part much faster than if we put it through a normal RTM or injection resin process. So these hard parts that are coming out being used in aerospace, being used in airplanes, satellites, and other different automotive applications are all textiles. They're not necessarily metals as we think of them anymore, just because the textile has more shapeable and higher strength to stiffness properties. So now we get into Smart Textiles. So here we have a circuit board. It's an off-the-shelf Adafruit board, nothing fancy. It's not designed for the process. And we've stitched into it with conductive thread. And I have a colleague also in Germany that works on a lot of this type of stuff. And we do this up here in Seattle regularly for different tech companies. But there's some advantages of conductive thread stitching as opposed to wire embroidery. With conductive thread, we can actually stitch directly into the hole and make electrical connections so that you don't have to solder things later on. And this means that we start to be able to put boards down in a fully automated way. So when we start with small boards and test boards like this, that's one thing. But when we start looking at scalable smart textiles and how to put these very complicated boards and circuit patterns together, this is an exceptional technique for being able to do that cost effectively and quickly. So here we have a variety of different conductive threads that we've tested. Different conductive thread companies send us materials regularly and we'll try it. And that way we can make different data sheets for people and be able to test how these conductive threads work in our equipment. And that way we can run them faster and make different things. So again, here's a couple of different circuit board stitching, as well as different type of metamaterials, patch antennas that can be designed. All of that allows us really to work with the textile structure. And so one of the interesting things that I think is in this type of embroidery is looking at how geometry responds to the frequency response of e-textile. So for instance, if I have an antenna that is a circular antenna or a flat antenna like this, it doesn't behave the same as when I crumple it up into a small ball. If I crumple it up, it has a different frequency response. And so this really allows us to start playing with what the textile does depending on what the shape is. And so we can theoretically start to have textiles that you can fold and have a different output response than when you open them up. And this opens a whole door for different smart textile antenna systems. So I think this is a very open area of research right now. Here we have other circuit boards off the shelf. So this is a LilyPad Arduino. This is a Circuit Playground Express. All of these are just off the shelf Adafruit boards that you can get online. And we can use them very easily in the embroidery machine. It stitches into them. It creates all the electrical connections and also creates these pads going throughout the entire piece so that you have touch sensors, which is another wonderful way of being able to interact with the textile. So we can use things like textile jigs. So you'll see here that there's height on each of these. And that allows us, if we're doing a more manual process, to be able to use something called applique. And applique means I'm going to take one piece of fabric or a circuit board or some material, put it on the embroidery machine on another piece of fabric, and then stitch the two together and go around that. And this can be used for design. This can be used for technical applications. It's a way of fusing two different materials together. So I had one interesting project where we fused essentially sewer grates to a piece of textile. And so you can start to stitch into a sewer grate onto an embroidery machine, which is just a fantastic technical opportunities there as well. So here we have a Smart Textile piano, and this is something that comes exactly off one of the embroidery machines. There's no human after this is done, and it creates all of these capacitive touch sensors, which lets you play the piano. It creates the wires and the wiring that connect the piano sensor to the circuit board, and then it covers over the wire with a protective plastic coating. And then it also puts the USB cable down and stitches that down as well to help create strain relief so it doesn't tear out or tear parts on the circuit board. And we even have now equipment that can put circuit boards down on the machine, some robotic arm that feeds the boards down. So we don't even have to worry anymore about putting circuit boards down. It's a fully automated process, which lets this be a highly scalable, highly adaptive process. So this is another piece of Smart Textile now that is very easy to scale. And again, it's a pillow here, but your imagination is what you can do with this or what you could put this into, whether it's carpet squares or curtains, or it could be resin infused to create hard dashboards. It's up to you what you want to do in that space. Here you'll be able to see one of the embroidery machines in the middle of stitching, and that way it can start to stitch down that circuit board into a piece. This one's a fun project. This is an automotive dashboard thinking about what might the future of Uber look like. So I have a colleague over in Germany who's an expert in leather embroidery, and we worked with her to do this. And this is an incredible part that lets you do swipe sensors, touch sensors, and then we can interact with different parts behind here. So the idea being that we have two layers. The first layer is for leather embroidery, and that way we see what we're interacting with. You'd put your cell phone down here, and that syncs the textile to your cell phone. And then underneath of this, we have all of the electronics in one sheet. And so here you'll see touch sensors on the right-hand side. You'll see a swipe sensor on the left-hand side. You see a circuit board that we designed to be able to do different circuit board integrations. And then here you'll see actually something interesting called an LED sequin, which we're going to get to in a moment. But essentially, this ensemble lets you start to work with textiles to build whatever electronics you want inside of them very quickly and very cost effectively. So this is another project done with Hochschule Niederrhein over in Germany, doing an interactive jacket that as you pin this jacket together and touch different aspects of it, it starts to make different sounds and interact with the user in a different way. Again, showing that sometimes simple interactions are the best. So one of the things that I remember from previous research and previous studies was that if you have a lot of extra things that you have to do to get it to work, people don't want to use that. So what that means is if I have to open a patch up and put something inside of it, or if I have to like turn something and then feed this cable through, people don't want to do that. But if I can just put it down and clip it or zip it or Velcro it, people know how to pin a shirt together, and that's not an extra barrier to usage. And so there's a lot of plays in these very simple ways of being able to interact with textiles that I think are very important to focus on, as opposed to some of the more complex ones. So here you'll see as you start to pin the shirt together, it's going to start to make different sounds and interact with you in different ways. Now, here's where we get back to those LED sequins I talked about. So I think this is the coolest of cool in textile. So if you look, a sequin is a small plastic circle. It's a small little piece of plastic that we can use for ballerina dresses. We can use them for flippable sequins to make different patterns and designs. There's a lot of usage in them for different New Year's attire. But a sequin to me is a single-sided circuit board. It's something where I can start to put components and electrical components down. So if we look over here, you'll see we have a sequin that came off the same kind of sequin reel, only it has an LED on it. And now we can start to use this attachment that can put down 500 sequins a minute. And we can start to put down a whole bunch more of these small electronics, and we can pick and place which ones we want. So maybe we want grids like here of different LEDs. Maybe we want a grid of temperature sensors spread out. Maybe we want temperature sensors, LEDs, oxygen sensors. Now we can start using the embroidery machine to put different complex electronic components down in grids so that we can build up these very intense and very interesting smart textiles. So my favorite example of this is, imagine you had a wall, and in this wall, you're trying to create a wall that has some interactive feedback. Maybe it can notice when people walk by and wave at them. So right now, you could do that with circuit boards. But if you did that with circuit boards, you're going to have to buy circuit boards that you connect together behind a panel, and then you're going to connect all of these. Each one of those has essentially a little tiny light sensor that detects if you're shadow or whatnot. And that circuit board will be a huge piece. So you can never get one giant wall made at once. It's not going to happen. But maybe you could start to get a smaller piece, and these smaller pieces parallel together, but it's still going to be very cost effective because you're going to need 100, 200 boards to kind of connect. Now imagine if you go to some guy who has a big embroidery machine and he makes, I don't know, curtains for a living. And you tell him, I want to put a whole wall of these grid sensors into something the size of a wall, a curtain. Well, he's gonna say, it's quite doable. Like, you have the LEDs, you have the connective thread. We can do this. It's just like doing a normal flower motif on a curtain. And now suddenly you can very cost effectively create these very large grids or these very large interactive flexible structures. And I think that's a really cool opportunity using these sequins. So I'm particularly excited about where this goes in the next few years. I think there's a lot of interest from startups and tech companies combined. And how can we use the textile equipment to be able to create a pick and place so that we can start to put these things together in these complex and interesting ways? And then last of all, I want to keep this side. This is a collaborative project between ZSK and Jackie Puzzi, looking at, we're in embroidery. So a lot of the slides I showed here are very technical, but we step back for a minute. Embroidery is beautiful, and that's really what people want too. So if you're already doing technical things, why not make them beautiful and start to work with it? So I think Jackie has done a fantastic job at working to create some of these different design motifs that are just beautiful. Her work is wonderfully done. But in this one, we start to see a fox that has LEDs in the eyes that have interactions. And these could be connected to circuits that allow you to change them based on different inputs or outputs or other different smart textile parameters. But this lets us start to look at, beautiful embroidery as well as technical. And I think that's a really nice spot to kind of leave this from a design standpoint. How can we use an embroidery machine that has been around for a long time, but they haven't had the same level of detail or fidelity or other different aspects about them? But how can we use these embroidery machines to start to create these new and interesting textiles that do things, that have function, and also still delight the user? So I think I'm at that half an hour mark where I want to leave a little bit of time for questions because I always get a lot of interesting questions. This presentation is actually up on my LinkedIn. If you ever want to see it, you can go through and see that if you go to Topher Anderson, you can go home. And it is right here inside of my presentation as well. So we can talk about that and we can go through a little bit below. I also have another presentation on a guide to technical embroidery, which gives much more technical capability and shows you some of the different things that you can do at a more technical level in case you're looking at how different things in embroidery are called or how they interact, or more details about pantographs and roll-to-roll units and how to be able to manufacture parts quickly. So I'll open it up for questions here.
Topher, that was fantastic. Truly such a master class in what you do. Thank you for that. Kind of a wonderful peek in. So as a reminder to people, feel free to put questions in the Q&A and we will take as many of them as we can. One of the questions that has come in is, could you speak to how your educational background led you to where you are at this point? Like, can you walk us through, because you shared that you have a background in biomedical and textile engineering. So how did you get from there? And was undergrad, what was grad, what was your doctoral research? Like, how did that all bring you to the place you are now?
Great question. So I think actually there were a couple pivotal projects and processes in undergrad that kind of started to point me to more technical. So in undergrad, I was actually architectural engineering or civil engineering. And I had a professor who did a lot of different work in textiles, Dr. Pastor, a fantastic resource for textiles. And we'd work in the research lab doing braided stents and some other projects. It just started to open up my mind about what can you do with a textile that I wasn't exposed to before that. And then in the last year, actually in undergrad, I took a class actually with Marcia doing jacquard weaving. And that also opened up a whole nother set of smart textiles. We'd made some smart textile jacquard breadboards for putting electronics in with a classmate of mine, Megan Foley, who's now down south at Nike, actually. So those were my two opening projects where I started to see that there's a play here and there's not a lot of people doing it. And so I went over to Germany to grad school over there because they had a very large biomedical and engineering school. It's called RWTH Aachen University. It's I think 40 some thousand students, most of them in engineering. And I loved it. And so I started working on bioelectrics, looking at actually textiles to make electromagnetic interference shielding for MRI and positron emission tomography, so medical imaging, essentially making textiles that allow you to start to understand where cancer is located in somebody and better allow the doctor to find where that cancer is. And so that opened up this technical textiles. And that's where I started actually using ZSK's equipment back then as well. And then after that, I came back to Philadelphia and started my PhD in textile engineering at Jefferson University. And I had a blast. I started seeing textiles as not just a visual, but an interesting way and a very sometimes difficult way of interacting with these complex shapes and complex mentalities. So a lot of my PhD research was in textiles that could be made for artificial skin or tuning these complex mechanics for textiles so that you have different mechanical structures and the mathematics behind that. And so I started doing that, and then I started teaching actually at Jefferson. I loved teaching. That was a fantastic thing. I taught a whole bunch of electrical engineering courses. And shortly after that, somebody from Lockheed Martin came and called me out. So I moved to Denver to make electronics for spacecraft and work on the electronics packaging team there, doing different types of electronics for satellites, spacecraft, that type of thing. And then after that, Microsoft actually called me up. So I went out to Microsoft's Applied Science Group, and we did different flexible electronics for them as well. And I just kind of fell into this niche that starts to be that a lot of engineering talent, a lot of people have gone into things like software, because every day we're inundated with Bill Gates' success, Mark Zuckerberg's success, all these other companies' success. And I think that's left a really nice play inside of things like textiles, where it takes a little of effort, but there's so much stuff you can do in the field. And now, I mean, now I'm in complete happy. I'm in bliss. It's a perfect combination of visual design, of making things that are beautiful, but also putting technical things in, whether that's smart textiles and electronics or things like composites. So for me, it's a little bit of a windy path to be able to get here, but now that I'm here, I don't think I'm going anywhere for a long time. It's like play to me, and I think that's the most important part that you can get. So
I love that concept that it's essentially play, and that and of course that does drive you forward. So that leads directly into a question that we've had from multiple people. What's the most exciting or tantalizing opportunity you have encountered?
Ooh, there are some really interesting opportunities right now in shape memory alloy textiles and flexible robotics. And in undergrad, I had done a little of this research, but I start to see the doors now for things that you can do, like having a napkin across the table and crawl across the table so it can move, or having wings of a blimp that can actually change in response to their environment. Or another one might be a curtain, and the curtain maybe has Nittmal-Meyer in it so that when it's sunny out, it closes, and that way all the sun is reflected back out and it doesn't warm the space. But in the winter, when it's colder, those apertures open and let the sunlight come through and warm the space. So I think shape textiles are an incredibly important part, an incredibly interesting part upcoming that hasn't really been explored. I think there's some also very interesting niche ones upcoming too. So I just did a project for fun in the gardening space, creating textile gardens that you can unroll with everything inside of them and wires and everything else that comes with that. And I think that would be a really fun space as well to explore. And that's something, if somebody wants to work on with me, reach out and we'll gladly start a fun project up together to explore it. But There's some also really interesting ones behind closed doors I can't go into right now. I think you'll start to see some of them from different tech companies popping out in the next, quite frankly, next maybe year or two. Some of them are already in development and in scaling, which is exciting. So keep your eyes open, that's for sure. There's a lot happening in this field across the entire world, yet alone across different companies here in the US.
Well, that's exciting. We will stay posted to see what comes. And I know there's quite a number of gardeners in the meeting today, so I think you're going to get lots of
Reach out.
Here's a great question. Are there any restrictions on the fabric type? For example, can we embroider on compression garments?
Cool question. So fabrics, that the way I have learned now with embroidery to think about fabrics is way different than I did as a textile engineer. So to me, a fabric now becomes things like saran wrap as a fabric, aluminum sheet, aluminum foil as a fabric, things that are not gelatin sheets are a fabric, things that are not necessarily traditionally fabric oriented. So when we start getting to things like knits, definitely we can embroider into them. Things like compression goods, a lot of different warp and weft knits all have different mechanical properties due to the way that they were created. Different, essentially, we call it elasticity. A lot of them have different orthotropic elasticity, which means they have different stretchiness in two different directions because of the coarse and wale structure that was used. And because of that, we have to look at that a little bit whenever we're embroidering. So for instance, let's just say a fabric starts to warp and change on the embroidery machine. That could be a potential problem for something when I'm trying to stitch into a circuit board. But CSK is clever. We came up with different camera systems that let you track how things are warping on the embroidery machine, such that we can subtract those out. And the embroidery machine can essentially remove all of the motion in that textile. And that allows you to have high accuracy. So something like a compression sock, a compression garment, yeah, that's relatively straightforward at this time. If you're trying to put wires in it, we have techniques that allow you to start to wiggle wires through and to be able to create areas such that you can stretch the fabric. Because if I put a wire straight down a piece of fabric, there's not going to be much stretch there because all of that stretch is going to go into the wire, and then the wire is going to break. So we have techniques that allow us to ensure that we have stretch such that the wire and the fabric stretch at the same time. I think that's a fantastic opportunity there to be able to do things. So things like yoga pants material, piece of cake. We've done a lot of projects with that, different athletic garments, athletic goods. Yeah, that's fairly straightforward. It gets more tricky if you're starting to do non-standard materials. Things like balsa wood is a kind of trickier one. Stitching through very thick aluminum, like aluminum flashing, can be a little tricky. Sometimes extremely thin ones also, because they tear. So electro spun fabrics are also quite tricky. We have techniques for it, but again, electro spun fabric is like a fourth of the weight of a tissue paper. So they break very easily. So we have to very carefully reinforce them so we can hold down. We've done different stitching into PVA and water soluble fabrics, or thermogaze, which is a fabric that goes away with heat. And so that allows you to start to build up lace structures. So there's a lot of plays inside of that from a fabric standpoint, how I see fabrics now that I didn't beforehand.
What an interesting broad definition of textiles or textile substrates.
It's open.
Well, this next question speaks to sort of addresses a little bit of what you were just speaking to, which is sequins come off all the time on costumes. So how do you protect sequin sensors?
Great. So sequins themselves, there's different ways to stitch sequins down. And in general, if you're on costume sequins, you're in a very low cost sequin. And so what people do, especially when you're manufacturing, they'll do one single stitch in the middle. And on lower quality machines, that single stitch isn't enough. On a higher quality machine, that stitch will hold the sequin in place. But even so, by increasing the quality a little more, we can do 2 stitches or 3 stitches, or create different areas of higher stiffness in those sequins. So what I do with electronic sequins, because the value is much higher, as you allude to, in compared to a plastic sequin, I actually have techniques to be able to create the sequins and stitch down on both sides of them. So that locks the sequin down into the fabric very secured. And that way the sequin really is embedded. And then to make it even more interesting, we'll do something called a bowl stitch over top of that. And a bowl stitch is essentially a star of normal thread at the very end that goes and really locks the entire sequin down. And we could put 50 different stitches if we want on top of that, really permanently fusing that to the fabric. And we do that quite often because it protects the sequin from getting damaged from friction or abrasion. And it also looks a little nicer instead of having a sequin edge that might not be as nice. So in that regard, there's a lot of plays there to be able to hold that down. And there's also, I've done a project where we put epoxy on the top of the electronic to kind of smooth it out. And that allows us to have less pull or less friction or abrasion on the sequin as well. So I feel it's a very good question. And there's a couple ways forward if we wanted to attach these sequins in a very high quality method in a high quality way.
And what it says is that you're adjusting the techniques and the processes depending on the material, depending on the end use, depending on all of the parameters.
Yes, and I think that's actually I wouldn't say a cop-out answer, but a common thing in that the technique that we use very much depends on the end use. Are you going to wash that smart textile or not? Is this textile have to stretch? Is it single use? Is it have to be recyclable? What level of temperature and current are we sending through it? So all of those actually really much guide what materials we use, what subset of materials, what fabrics. For instance, if we're going to do something with a very hot heating wire, we probably don't want to use a polypropylene fabric because of the low glass transition temperature of that. So maybe in that case, we want to use Teflon fabric or PTFE with a PTFE thread because it has a really high temp. Or maybe if we have something that has to have a lot of mechanical strength, maybe we don't use polyester thread, but we switch to Kevlar thread. So again, there's a lot of plays that do come up, but in general, you can kind of get the right idea for the end use. And usually you can get even a couple parts off. I call them early stage prototypes, where you can get all of the technique, you can see how it works, and you just don't put the high temperature through it till you're ready to. And when we go to that, then we get the professional materials and we make it.
Really interesting. And this next question, you touched on this just a bit. So what are the ideas in terms of solving laundry issues and sustainability issues with smart textiles?
I love these. So laundry issues are probably my number one question, especially at tech companies, because they're looking at smart textiles. And interestingly, I would say this really doesn't bother me much anymore. There is so much research in this and there's so many different techniques. There's techniques such as overmolding, where we take the electronics and we can encase them in rubber. And then we have little connectors on the back that are magnetic connectors. There's techniques that allow us to wirelessly beam data in between two different pieces such that we can completely close them from water. If you think of car seat heaters, I mean, car seat heaters are designed in such a way that you can spill your water on your car seat while you're driving and you don't get electrocuted. And that's been pretty well established that those are in many millions of cars. And that's something that they've looked at already. So I would say the proof of concepts for that are already very much present, and it doesn't really bother me too much. There's different coatings. There's hydrophobic coatings you can spray onto a circuit board. There's methods using wires and encasing your wires in plastic. Or even, I think more elegantly, you just let it get wet and you design your circuit in such a way that it takes a reading when you put the jacket on. And that jacket reading listens to the resistance in each of the wires. And, if there was a little bit of wet or it was a little dry or a little scraped or something came off, it just adapts to it in code. And that way software is a lot easier to change than putting a new wire into a piece of garment. So I think there's a lot of plays in that washability space. We've done testing in-house for at least 50 wash cycles. One of my colleagues, Melanie, is working on her PhD over in Germany on that exact issue of how to wash textiles with smart textiles and how long that they work and how long they last for. And I think it's fantastic piece, and she has great data. I'd reach out to her if you're interested in that, of essentially what level of resistance increase happens as you wash through different various wash cycles. It's a great body of research. As for sustainability of textiles, I love that question. That's something I've tried to push pretty heavily personally, because in my mind, you're taking two of the worst polluting industries on earth, the electronics industry and the textiles industry, and you're combining them. And that's never a good thing when you combine bad things, because the complexity changes. You're increasing complexity of that final product. So my personal pitch would be that, I would love to see us start to move towards a standard that allows us to start to make smart textiles and label them in a government database such that we know what materials are in them. We know that there is recoverable polyester in this. We know that there's silver that we can take out, and the circuit board has gold plating on it. And that way a recycler can just scan it really fast, know what's recoverable out of that process, and then start to recycle and reclaim some of that material. I think that's kind of required, because if we start to use electronics in some of the fast fashion that we're using now, you're going to start to get circuit boards and things in a shirt that might only be worn 2 or 3 times. And I think that's a step in the wrong direction from a sustainability standpoint. Now, if there's a way to reuse that and reclaim the material, and a lot of the silver threads and other things have value to them, so it's not out of the question. I think there's a lot of opportunity for socially responsible companies and startups to be able to explore that particular space. And I know IPC, which is a circuit board standardization committee, is looking at some of those standards. And we've worked with them in the past to try to push some of that. And they're very happy to start to look at that. But ultimately, I think it needs to come down to some type of a regulatory body or a group of companies that say, you know, we're going to do this properly. We're going to try to use the same type of fabric. We're going to try to use these standards so that we know what's recoverable. And then maybe we even have a closed door life cycle where we can ship back used ones and we can reclaim parts from them. So that's where my hope is. It takes a lot of different players working together, and quite frankly, a lot of young textile designers and textile engineers to agree to that. That's where really the change happens, because if somebody doesn't propose it in a staff meeting, people who have been doing it for 30 or 40 years aren't going to propose it. So that's where I'd like to see that heading, and personally.
Well, that's an exciting direction, and I agree. It's the next generation who can bring that forward. So
yes.
And the fact that the question came up multiple times is fantastic.
Makes me happy. Makes me very happy. And I mean, there's so much in the sustainability space that we can do. I generally tend to very much like embroidery because it's a finishing process. And finishing means we only really use the materials that we need. And there's not really so much waste material in that process. And that's something that I like. There's always a little bit of waste, but comparatively to some of the other processes, I'm very proud of that. And I think that's a very strong thing to stand by. But we need to do more than that. That needs to be not just a one-off piece, but that needs to be something that we start to look at sustainability also from a local sourcing standpoint, instead of shipping things left and right and buying fabrics that get shipped 5 times from different places. But can we make them here in the US? And there's other companies I've worked with too. Cotton Ink is a great one, trying to create that life cycle inside of the US, trying to be able to have a ecosystem that we use that is based on cotton made in the US, which I think is a wonderful thing that we need to get back to. So there are plays and people there working on that for sure.
Well, it's exciting to hear that. One of the questions that came in is, how can startups work with you?
Yeah, great question. So I have a website. It's called zskacademy.com, and that'll point you to the correct one. And here you'll see there's a bunch of different options. Actually, let me pull it up real fast and I'll show you. It's pretty straightforward. Let me grab this. I'll pull up a new tab, zskacademy.com, and let me share screens again. Share screen 1. All right. So if you go to zskacademy.com, it'll point you over here to the host site, training.zsk.com. And if you go down here, I have different resources. And down here, we're going to have actually a video courses coming up for schools and tech companies if they want to start learning some of this. But I do have a couple ones that are currently open. And one of them is this sampling guide. And if you go into the sampling guide and log in as guest here, you can start to see I have different lectures available of how to work with us and how to send materials, how we can start to create a project together for early phase startups. I have tutorials on how to use Illustrator to create it and how to connect lines. So essentially this website is where I kind of host all of that info. So I love working with startups. There's a lot of startup projects that have gone quite successfully in the space, whether that's Smart Textiles or other things. The easiest way, just reach out to me with an email and we can go from there. And probably I'll send you this website and get you a name so you can sign in and add some stuff and start to peruse around of what's required. But it's a fairly straightforward piece, especially if you're trying to do wire embroidery or other things. I encourage it. I love working with students and people that are new in the space and teaching this. It's fun.
Fantastic. I do think you're going to get more takers after today's presentation.
Excellent.
We have many questions. We won't be able to get through all of them, but we're going to get through as many as we can. what are some of the limitations that you're running into? Can you speak about battery technology and power sources?
Beautiful. So you nailed it. Whoever said that one, you know what you're talking about, because that is the major limitation I come up with in smart textiles. And it will always be. It's the same limitation that we have when we design spacecraft. Um, Battery tech does not develop as fast as Moore's law. It's based on chemistry, and that's a very slow and arduous process to develop. So in that case, I've seen a lot of different research publication papers about energy harvesting textiles. It's cool, but I've yet to see one that we could actually use in practice that generates enough power to run a small circuit board. And so therefore, batteries will be here to stay. And so batteries, I think the correct way to work with them is to design the battery in such a way that it doesn't really bother the user, that it's light enough, that it is tucked in a design way that they don't really notice it, which comes down to essentially a user design, industrial design, textile design, fashion design in that case. But it's a really hard problem to solve. I've seen some flexible batteries that are interesting, and I think that tech is developing very quickly, but it still doesn't have the energy density of a more rigid lithium ion battery. So hopefully some of this will get better too, with autonomous car companies putting a lot of research and funds into developing better battery tech. But batteries always hold smart textiles back. There's no question about that. The best I have right now is using USB batteries, small USB battery packs, and cell phone batteries, because they're very available. For things like sensors, Bluetooth, Wi-Fi, piece of cake. For things like heating garments, they can use battery really fast, because thermal energy is essentially one of the worst efficiency uses of electricity, and so it's going to suck up a lot of battery power to make your gloves warm, and so that's where we start to get some problems there. But that is an active area of smart textiles research, is batteries and flexible batteries and textile batteries. Very difficult research though.
Well, interesting and great that our attendees, at least one of them, knew that was an
You nailed it.
Next question. Can you introduce the development for thermoplastic carbon fiber?
Yes. So thermoplastic carbon fiber is a fascinating thing. I've seen really spiral up in the past 2 or 3 years. There are companies out there that will take a carbon fiber tow, which is again just a bunch of filaments that are bundled together, no twisting or anything else. Then they take the tow, they open it up, and magically they put in different plastic fibers and close the tow. So when I get the tow material, it is just like a textile. It is flexible. It feels just like the original carbon fiber tow. But when I hot press it, that's where those fibers start to fuse together and consolidate, we call it. And that's what allows us to turn a very flexible soft part into a very, very rigid part. And so in that case, you start to be able to do things that you couldn't do before. So for instance, previous to this, if I was just using carbon fiber, I could inject liquid plastic into that, and that's what creates the hard surface that doesn't bend. But that plastic or epoxy takes 20 minutes to 24 hours to cure, and that's way too slow for the mold. So it's a very expensive process. With these hot presses, I mean, depending on how hot your press is and how much pressure you have, theoretically, you can pump these out every couple minutes, one of these, even faster, and you can make them in scale. So the cost effectiveness is something that has never happened before. And whenever that happens, I see a lot of development and a lot of interest and a lot of new products come out of it. So that could be things like drones, that could be things like shoes, that could be things like different sportswear and sports equipment. There's, again, sky's the limit for what you use that part for. But ultimately, it's an extraordinarily strong and stiff part that weighs very, very little.
Wow, so interesting. And we'll make this question the last one. So my apologies to everyone for whom we did not have the chance to get to your questions. I encourage you to connect with Topher on LinkedIn, go to his ZSK Academy site. So one last question and a comment that has been echoed multiple times is, thank you for the eye-opening presentation. What yarn properties does the embroidery equipment ask of conductive yarns? There are many new conductive materials emerging. Would appreciate if you could share your experience working with conductive yarns.
Great. So that is a really good question. And there are a lot of really bad conductive threads and yarns on the market. Some of them are too hairy and the hairiness qualities are too much. Some of them are too thick to run in industrial embroidery applications. Some of them just aren't conductive enough for different applications, and some of them are conductive, but they have too low of a tensile strength to run. So really, this is one of those answers that would be, it really depends on your application. And that's something that you can reach out to me and we can chat about, because the whole space of thread making and thread construction is an enormous field. And there's a lot of research, and it's an active body of research too, on how to make a very high quality conductive thread. We have different materials. There's different twisting processes that can be used. There's covering processes. There's different lubrications that depend. Again, sometimes if I'm doing a composite and I'm putting conductive threads inside of that, then I have to be careful that the conductive threads have the correct lubrication so it doesn't ruin the composite. If I'm doing something with electrodes that are going to touch the skin, maybe the electrode has the correct impedance match, but it's not soft enough and it scratches against the skin. So there is an enormous body of research and active research inside that field. So I would say reach out to me with more specifics. I can kind of guide you. There's a lot of companies that are making good quality conductive threads and nice quality technical materials. It depends which one you're looking for which application.
Well, fantastic. So Topher, thank you so much, Dr. Topher Anderson. That was amazing. We appreciate everyone joining us today from all over the world for your presentation. Thanks so much. Thank you, Topher, for a brilliant presentation.
Thank you very much. If anybody wants to reach out to me, my email is the easiest email. It's the letter T at zsk.com. So T is in tiger, at Z as in zebra, S as in snake, K as in kangaroo.com.
Perfect. Thank you so much. Everyone have a great day, evening, or morning, depending on where you are in the world.
Likewise. Bye, everyone. Thank you for joining.
Bye.